Welcome, ladies and gentlemen, to your video lesson for 6.4. This is transforming linear functions. This is the first activity in your packet, and there were some pages that were missing. And if you're watching this and want to get those pages, make sure you one of two things. You can pause the video right now. You can email your teacher and ask them to send you the packet. Watch it when you get the missing pages, or you can check your email because it was emailed to you earlier in the semester here. So the goal today is to be able to get really good at taking our y equals mx plus b function and understanding what m really does and what b really does in terms of a transformation. Really, today is about learning vocabulary that's attached with what happens when I change this number and what happens when I change this number. There are some keywords that we assign to each of those scenarios, and so that's what we're going to get out of this activity. All right, so for the warm-up, I'm just going to quickly go through graphing these. It says graph the following lines in the graph below. You may want to use a different color for each graph. So the first one is y equals negative 3x plus 2. Remember, the number that's all by itself is the y-intercept, and you will always graph the y-intercept first. So I'm going to go to positive 2 on the y-axis. That is my first point. Then the number that is attached to x, that is your slope. And then remember, we want to turn negative 3 into rise over run directions, how to basically tell us how to get to the next point, right? So negative 3, if it's an integer, you always put it over 1. What that tells me is that because it's negative 3, that tells me I'm going to go down 3 and then to the right 1. And I'll do that over and over again until I get my line. So down 1, 2, 3, right 1, down 1, 2, 3, right 1. I'll keep doing that over and over again. Down 1, 2, 3, right 1. And notice that only gets me like half the line, right? I'm not going to say this every single time, but it only gives me the line on this side. And if I want to get the line over here, first thing is that it has to be within the same line. So how do I do that? Remember, I use those instructions exactly backwards. So instead of down 3, right 1, I go up 1, 2, 3, and then left 1. And notice my points line up with the ones I already graphed. Try to graph these as straight as possible. It's hard to do with the tool that I have. Do the next one in red. All right, now this is interesting because it appears as though it's missing some information, right? And the other one, we had plus 2, right? And that told us what the y-intercept was. But there really is a y-intercept already in this function, and that is plus 0. I can add plus 0 to any type of equation. It has no mathematical or numerical value to it, but when we're graphing, what it tells us is that the y-intercept is 0. And so that is the case here. And so I'll graph my first point at 0. My rise over run directions here are 3/4, which tell me to go down 3 into the right 4. So I'll do that. Down 1, 2, 3, right 1, 2, 3, 4. Move myself here. 1, 2, 3, right 1, 2, 3, 4. And then exactly backwards. 1, 2, 3, 1, 2, 3, 4. 3, 4. And I will graph that line. Okay. And I'll do the last one here in blue. No, I'll use green. All right, same idea here. We don't have a y-intercept, so I'm going to add plus 0. So my y-intercept again is 0. And now my slope is 5. I'm going to turn that to 5 over 1. And I'll get my rise over run directions. 1, 2, 3, 4, 5, right 1. Up 5, right 1. And then down 1, 2, 3, 4, 5, left 1. 2, 3, 4, 5, left 1. And I'll try to draw that as straight as possible. And those are our 3 lines, okay? So the big idea here out of those is that we really need to know how to graph in slope-intercept form. That's really like a key concept that we need to understand. So if that's something that you struggle with, signing up for a contact time is a great idea. All right, on to the activity here. So question 1 was actually not printed in your packet. This is the first one in the activity, though. And that's not really a big deal. This is something that we will start off with, though. Okay. All right, it says graph the following equations on the same set of axes on the right. When you graph each line, use a different color. I'm going to try to do that. And what we're doing here is we're basically, in the end, we're going to compare everything to the parent function. Now, I got to set up some information about what a parent function is. Okay. This is the parent function. If you notice, every single one of our graphs is going to start with a parent function, at least in the first two. And the parent function is essentially the simplest way you can write a linear equation. And this is something that we have to pay attention to, right? Y equals x is the same as y equals 1x plus 0. Remember, we talked about adding 0 to an equation, adds no numerical value, but tells us where the y-intercept is. And the other part of this is that if I write just the variable x, typically we don't write the 1 in front of it. However, when we're thinking about slope-intercept form, that tells us that the slope is 1 over 1. Right? And so we don't write either one of those things if we're trying to write it in its simplest form. And so that is why it appears as just y equals x. So again, y equals x is really the same as y equals 1x plus 0. We just don't write it that way because it's not necessary. Okay, so I'm going to go ahead and start graphing some stuff. And hold on a second. I'm going to go ahead and pick a color of blue here. And we're going to graph. All right, so y equals x. All right, remember that's 1x plus 0, so my y-intercept is 0. And then I have a slope of 1. All right, up 1, right 1, up 1, right 1. And that's a point. I know it's going to go down to here. And so that is our parent function that we're going to compare everything to. All right, and now notice some of the changes, right? The slope does not change here, and the slope does not change here, but my y-intercept changes for both of them. And so that's where our comparisons are going to come into play. Now I have a y-intercept of positive 3, and I still have a slope of 1. So up 1, right 1, up 1, right 1. I know that I'm going to be following this kind of line. So where do I end up? Right about there. Kind of following that pattern down this way, and we're right about there. So my line looks something like that. Okay. Now I will choose a green color for the last one. And again, my y-intercept is now -5. So -5, 1, 2, 3, 4, 5. I got counted again. 1, 2, 3, 4, 5. And same exact slope. So up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. Kind of following that same pattern all the way up. And then following it down, my line looks like this. Okay, the more points you put on a graph, the more accurate your graph is going to be. All right, now we have some questions that we got to answer about this. This is what the lines have in common. What they have in common is the slope. They all have the same slope. Slope is equal to 1 or 1 over 1, same thing. What's different about the lines? Well, the difference is the y-intercept, right? And so that's what's different about all of these. And now we're going to investigate, like, well, how does that actually make a difference in the graphs, right? So this question, how does the line y equals x plus 3 compared to the parent function y equals x? And this is where we want to talk about the language we're using. How is the line shifted vertically? Okay. So these are the two lines we're talking about for that question. And so how are the lines shifted vertically? It's shifted up 3. Okay, it shifted up 3 from its original position. How does the line y equals -5 compare to the parent function? Well, that one has been put down 5 spots, right? The whole line has shifted down from its original position. So we'll say it's been shifted down 5. And that's what we see in the graph. Now, if we look at just the equations itself, it's like, well, how do I tie what the equation says to what the line looks like, right? Well, like this one here, the first one, we said it shifted up 3. Well, that's because it had a y equals x plus 3. So the y-intercept was 3. The slope didn't change, so we shifted the graph up. So essentially, the y-intercept tells us what our shifting is doing as we go up and down the graph, okay? Now, the next question is, kind of using that observation without graphing, how would the line y equals x minus 2 compared to the parent function? Well, if my y-intercept is -2, and this one was -5, we said it shifted down 5. Well, this one means it'd be shifted down 2. Okay. And so so a new kind of vocabulary word is this idea of shifting. It all relates to the y-intercept. So whatever the y-intercept is, we just say that the linear, the line shifted up or down that much, right? So if the y-intercept is plus something, then we say it shifted up that number, right? If the y-intercept is minus something, we say it shifted down that number, okay? And so to that point, I'm going to move this for a second. Page, it says write an equation for the graph that has been shifted up 8, right? So now we're just saying like, all right, well, what if a graph shifts up 8? What would that equation look like? And so we're not changing the slope. So it's still y equals 1x or y equals x. And if it shifts up 8, then we're going to say it's adding 5. Okay? That's the first question, and it's all about shifting it. And the way we shift a linear equation or a graph of a line is by adjusting the y-intercept. We say it's shifted up or down based on what that y-intercept is, positive or negative, for the numerical value there. All right, next question. Question 2 says, graph the following equations on the same set of axes on the right. When you graph each line, use a different color to represent the graph. And I thought I already graphed this, but I guess maybe I didn't. Okay, so this one here, y equals x is already graphed for us in black. Awesome, don't have to do that one. I'll do the y equals 3x in green. Now notice each of these would have a y-intercept of 0, but it's not listed there. So again, it's for the same reason, right? If I add 0 to an equation, it has no real numerical value. It does tell us where the y-intercept is, so we just have to know that it's actually there. So if I'm going to graph y equals 3x, that means I go up 1, 2, 3, right 1, up 1, 2, 3, right 1, up 3, right 1. I'm good there. I'm going to go exactly backwards, 1, 2, 3, left, 1, 2, 3, left, 2, 3, left, and there I am. So there is that line there. I'll change colors. Maybe I'll use orange. Why not? All right. So this one here, I have 1/4 x. So that means I go up 1 and then right 1, 2, 3, 4. Up 1, right 1, 2, 3, 4. And then exactly backwards, down 1, 1, 2, 3, 4. Down 1, 1, 2, 3, 4. All right. So there's that line drawn. Now, observational questions here. I'm going to switch colors. I'm just going to use black, I think. It says, what do the lines have in common? Well, what do they have in common is the y-intercept. The y-intercept didn't change at all. Y-intercept is equal to 0. Okay? What is different about the lines? Well, what's different is that the slope changed. Slope changed this time. Okay, so we kept the y-intercept fixed. They all intersected right here, right? We kept it fixed, and we adjusted the slope. Okay, and now we're going to talk about a different vocabulary word and talk about tallness of a line. How does the line y equals 3x compare to the parent function y equals x? All right, so remember this is the y equals x function. The green one is the y equals 3x. Well, to me, it looks like it's gotten taller, okay? And we can quantify how tall it has gotten because the slope is 3. The original slope is 1, right? The new slope is 3, so it's 3 times as tall, okay? It's 3 times as tall. Now we compare it to the y equals 1/4 x. So how does the line y equals 1/4 x compare to the parent function y equals x? How many times tall is it? Now this is going to be like a somewhat of a counterintuitive way to describe this, okay? But as we notice, the orange line here is not as tall as the parent function, right? It is less tall. And so we're not going to say that it's shorter. We're still going to say it's as tall. And so what we're going to say is that it is 1/4 as tall. And I think you can make sense of that. We can wrap our head around something that we've said, you've probably said it's like half as tall as something. One thing is half as tall as another, right? And that's something we usually don't use it with other types of fractions, but we still can, right? And so that's what we're going to say here. It's 1/4 as tall. So what are we getting at? Well, essentially, if we're comparing a new equation to a parent function, right? Whatever the tallness is, whatever the new slope is, we say that it is, the slope as tall, whatever that number is for the slope. So in this case, we said the slope was 3, so we said 3 times as tall. In this case, we said the slope was 1/4, so we said 1/4 as tall. All right. Okay, so now without graphing, how would the line y equals 7x compared to the parent function y equals x? Well, my new slope is 7, my old slope is 1, so that means it'd be 7 times as tall. Done. This here, page, come on. And then the last one here, writing the equation for a graph that is half as tall as a parent function. So y equals something, right? And it's half as tall, so that's going to be, this is essentially telling me what the slope is. It's going to be 1/2 x plus 0, you could write, or just y equals 1/2 x. Either one would be fine, okay? So this is kind of getting to this vocabulary word of tallness, and the slope adjusts the tallness of the graph. Sometimes, like I think sometimes the textbook uses the word stretched, and you can make sense of that too, right? It's been stretched upwards, or it's been stretched downwards, or compressed maybe. Those are other words that you might hear that describe the same thing, okay? All right, next question. These ones I have graphed already for us, so hopefully it'll save us some time here. So it says graph the following equations on the same axes. When you graph each line, use a different color, so I've done that already. And I have the y equals -3x graphed in blue. Notice the y-intercept is 0, up 3, right 1, up 3, right 1. It's there for us. And the red one is y equals 3/4 x. And that one is here. So it's up 3, right 4, up 3, right 4, all the way across. Okay? So let's start answering some questions. First question is, which line is steeper? Well, I think it's pretty clear that the line y equals, oh, I just realized I graphed a negative, I graphed the wrong slope. All right, hold on a second. I'm going to make some adjustments here. Boom. This is supposed to be a -3x. I graphed a +3x. So I'm going to change that. Still the same y-intercept. This is going to take me a second to just make some adjustments here. Boom, boom, boom. All right. So now I got that. So now it's going down 3, right 1, down 3, right 1, down 3, right 1. Okay. Bad. No biggie. Can't be awesome all the time. So here's the deal. Which line is steeper? I was going to say y equals 3x, +3x was the steepest line. So now that I've changed the sign, is that still the same answer? And the answer to that question is yes. It's still steepest, right? So here's the analogy that I usually give students. Like, imagine a set of stairs, right? And you're going up or down that set of stairs. Does the direction in which you travel change the steepness of the set of stairs? And the answer to that question is no. Of course it doesn't, right? You can't change the set of stairs. So sign does not make a difference in steepness. It is the actual, just the quantity of the slope itself. What we really say is the absolute value, right? The absolute value of the slope determines the steepness. So which line is steeper? Y equals -3x is the steepest. Does the negative sign matter when determining the steepest of the line? And the answer to that question is no. I guess I should have kept another one on there. Graph y equals 3x. So I'm going to graph that now. Y equals +3, up 1, or up 3, right 1, 1, 2, 3, right 1. This is getting graphed in black now, obviously. And so there we are. Down 3, left 1, down 3, left 1, down 3, left 1. And so there's that line there. And so we're asked the question here, y equals, which one is steeper, y equals 3x or y equals -3x? And the answer to that question is neither. They both have the same steepness because sign does not matter, okay? So I'm going to write that. Sign does not matter. Kind of out of space here. All right. Moving on here. Without graphing, which line is steeper? Y equals -5x or y equals 4x? Okay. We just said sign doesn't matter, right? We just look at basically we look at what is the biggest absolute value, right? And so what's bigger, 4 or 5? Well, obviously 5 is bigger. So which line is steeper? Y equals -5x. Because again, sign does not matter. All right. So that's question 3. Moving right along here. Question 4. Oh, that's not what I wanted to do. This is what I want to do. All right. Graph the following equation on the same set of axes again. I've already done that. It says when you graph each line, use a different color. Done that. You may want to label each graph on the line or create a color key. So we got them. All right. So I've already done that. And I've had them highlighted. So this is the blue line, y equals -2x plus 6. Y equals -1/3 x plus 2 is graphed in red. Actually, I got the colors wrong there. I'm going to do this. Move. Oops. I have the negative one in green. I have the positive one in red. No big deal. So y equals negative 3x is graphed here in green, and y equals positive 1/3 x plus 2 is graphed here in red. All right. This is a pair of lines in the graph to the right are reflected over the y-axis from each other, meaning the y-axis right here is a line of symmetry that when we fold the graph over the y-axis, the lines should line up with each other. What is the pair of lines that would be reflected over each other? I think this is pretty clear. It's the red and the green lines that are reflected over each other. And so we're going to start investigating like why does that look that way? Okay. So I'm going to grab my pen. Hopefully, nope, I got to change the thickness because we're on a space if I write like that. So which ones are they? It is y equals negative 1/3 x plus 2 and y equals 1/3 x plus 2. Okay? So in the pair of equations I listed in part A, what do you notice about their slopes? So same slope, but different signs. Maybe I should say it this way. I'm going to say it a better way. Slopes are opposites, right? One's positive 1/3 and one's negative 1/3, so opposites. And positive 1/3. Okay. So in the pair of equations that I listed, what do I notice about their y-intercepts? They are the same. They both have a y-intercept of positive 2. So that is actually a requirement. What the two things we just listed there are the requirements to make a line reflected over the y-axis, right? If I want one line to reflect over the y-axis of another, basically we need slopes to be opposite and the y-intercepts to be the same, okay? And we're going to adjust that slightly as we move on, okay? But if I want two particular lines to be reflections over each other, the y-intercepts are the same, slopes are opposite, that's all we need. Okay, so let's answer the question in part D. Let's write an equation of a line that would be reflected across the y-axis of this line here. Okay, what causes the line to reflect over the y-axis? So the equation is y equals 2/3 x minus 3. So what we said is that the slopes have to be opposite. So I'm going to need y equals negative 2/3 x. And the y-intercepts have to be the same. So opposite slopes, same y-intercept. So then minus 3 is what we would need. Okay? All right, moving right along here. Bring it all together. Now, describe the transformation on the graph. So this is what your independent practice and what your quiz questions might look like. So basically, here's what you got to do. You got to look at sine. You got to look at slope. And you got to look at y-intercept. Okay? Sine has to do with reflections. Okay? Slope has to do with tallness. And the y-intercept has to do with shifting. So those are the things that we're looking at, right? So part A, is it negative? And the answer to that question is no. So that means it is not reflected. And I'll move on to slope. Okay, slope refers to tallness. So how tall is this function? It is 1/2 as tall as the parent function. So it's half as tall. And now about the y-intercept. So the y-intercept is negative 3. So we would say that it is shifted down 3. Shifted down 3. Okay. So the next one, kind of following that same format. It is negative, so then we're going to say because it is negative, it has been reflected, right? Now, it is not an exact reflection because we don't only reflect it. We're also changing the steepness or the tallness, and we're changing, we're shifting it, right? And so it's not going to end up being an exact reflection, but we start off that way. We start off with the exact reflection, and then we do other stuff, right? So it is reflected. It is reflected over y-axis. And now look at the slope. The slope is 5. It's really -5, right? But we separate the negative from the slope. And so we just look at the absolute value of it, which is 5. So it is 5 times as tall. And then we look at the y-axis, or the y-intercept rather, and it is +2. And so we would say it's shifted up, up. All right. Then for 6, now we're doing the opposite, right? We're being told what the transformations are, and we have to write an equation accordingly. So we're taking this parent function and we're doing these modifications. So what's the first modification? It's 3 times as tall. All right. So I'm going to look and see if it also has been reflected, because if it's reflected, then I have to have a negative slope. 3 times as tall and shift it up. So it doesn't say anything about reflected. 3 times as tall, so it's just 3x, not -3x. It's been shifted up 4 units, so that's going to be +4. And so now, in comparing the parent function to this one, it'd be shifted up 4 units and be 3 times as steep. Okay. This one, 1/4 as tall, shifted down 4 units, and it's reflected over the y-axis. So it's because it says it's reflected, I know I have a negative slope. 1/4 as tall, so I know my slope is the absolute value of the slope is +1/4x. The overall equation is -1/4x, but remember those two different things. The negative reflects, the 1/4 makes it 1/4 as tall. It's shifted down 8 units, so then we say -8 or +8, however you want to do that. Okay, so that's all that we did in class. The next part of this is a bonus, which we're not going to get into because that's going to be something that pops up later, okay? If you really want to dig into this, what you need to realize is that perpendicular lines have opposite reciprocal slopes, okay? Which means that if my original slope is 1/2, then another slope is -2/1, right? The reciprocal is flipping the fraction, and one is positive, one's negative. And so I can just graph both of these really quick and kind of show you. Let's say the y-intercept for each of these is 0, right? So then I would go up 1, right 2 for the 1/2, up 1, right 2 for the 1/2, keep going, right? Boom. So this is that one. Now if I have a slope of -2, watch what happens. So I have the same y-intercept again. So I go down 2, right 1, down 2, right 1, down 2, right 1. I go exactly backwards. What you'll notice is when I draw this line, it's going to look like they are perpendicular, meaning they make a 90-degree angle, and they do. So that's what you get out of this, is that the slopes for perpendicular lines are opposite reciprocals, okay? And that's what you'd find if you graph them. You'd find basically 2 sets of perpendicular lines, okay? Cool. So independent practice listed here, right here. I don't have to read it for you. You can look at it yourself. I hope you guys have a great day. Adios.